Right, it's a pleasure. So welcome Dr. Chloe Griffin back to Liverpool. Chloe was an undergraduate here on the GPG programme from 2015 to 2019, and a PhD student at Liverpool from 19 to 2024, and now is a research fellow at the University of Southampton and a research fellow in earth science, computational paleoclimate. And so, yeah, welcome back. And today, Chloe is going to be talking about climate signals, climate cycles, and Snowball Earth glacial deposits. Thanks.
Yeah, so it's great to be back. Thank you for inviting me back. It's nice to be here. So yeah, I'm now down at Southampton as a postdoc. I've been there about 6 months. So sort of the work I'm talking about today, sort of what I've been doing sort of over the last 6 months on one of the projects I'm on. So we're going to basically talk about the climate cycles that we found in Snowball Earth aged glacial deposits. So just a bit of an overview of how this is going to look and what we're going to cover. So we'll start off with Snowball Earth, for anyone that doesn't really know what it is, and the hypotheses behind this, and then go on to sort of drivers of the Earth's climate system and sort of the problem that we are aiming to solve here. And then I'll introduce you to the Garvellach Islands, which are a really nice location to study Snowball Earth, and specifically an outcrop called the Garvellach laminites, which hopefully have the answer to our problem. And we'll go through a little bit of the sedimentology and sedimentological cyclicity of these. And then finally, we'll wrap up looking at the stability of climate cycles during Snowball Earth. So Earth has 3 climate states. So firstly, we've got greenhouse climate states, and this is where we have no ice on land or at the poles. Secondly, we've got icehouse climate states, and these are when we've got some ice on land and ice at both poles. And this should be a really familiar climate state to all of us, as it's the climate state that we're currently in today. And the Earth flicks really nicely throughout icehouse and greenhouse climate states throughout geological time, in a really relatively predictable and cyclical pattern throughout the whole of Earth's history. And this happens because the Earth has a number of sort of internal feedback mechanisms that take place, which prevent it getting too hot or too cold. So if we're in an icehouse climate state, for example, and we start to go too cold, those climate feedbacks can switch on or off respectively and push it towards a greenhouse climate state. But unfortunately, so there's periods through time where this natural thermostat that the Earth has breaks down, which then comes with a breakdown of sort of these internal feedback mechanisms, and we plunge into what's called a Snowball Earth. And Snowball Earth is thought to be when we have ice extending from the poles all the way down to the equator. And these climate states do occur through Earth's history, but they are relatively rare. So let's take a look back through geological time. To find evidence of our most recent greenhouse climate state, we don't have to go too far. We only have to go to sort of the Cretaceous period. And if we want to find evidence of the Earth's most rapid warming event, we also don't have to go back too far, only about 55 million years, back to the Paleocene thermal maximum, or PETM, where we have this really distinctive rapid warming conditions. After the PETM, the Earth gradually declined into our current icehouse climate state that we've got in this Quaternary period. But if we want to find evidence of the Earth's coldest time on Earth, we only have to go back 650 million years, which is quite nice, to find evidence of these Snowball Earth climate states. And just an idea of sort of the temperatures that are thought to have occurred around this time. It's thought that the temperature of Antarctica today is what was experienced around the equator during Snowball Earth times. And so this talk's mainly going to be focused sort of in the Neo-Proterozoic era. And this was a relatively important period throughout Earth's history. Pre-Neo-Proterozoic, there was no complex life, and the Earth's atmosphere wasn't anything like it is today. And then towards the end of the Neo-Proterozoic and up into the Cambrian period, you've got this real explosion of Earth's life that we're all familiar with. So zooming in a little bit further into the Neo-Proterozoic, we've got evidence of 2 Snowball Earth glaciations during this time. And this is thought to be the only time period during Earth's history that we've got evidence of this climate state. So whilst there's two Snowball Earths evident during the Cryogenian, there is thought to be another during the Ediacaran period, slightly younger than that, but this is more contested. So we're going to focus on the Cryogenian. So these two glaciations that occurred have called the Sturtian and the Marinoan glaciation. Starting with the Sturtian glaciation, this was thought to be Earth's longest and most extreme glacial period, lasting roughly 60 million years from sort of 717 MA down to 660 MA. And this extended glacial period was thought to have real implications on the Earth's dynamics. So the Sturtian glaciation ended relatively rapidly, pushing us into an interglacial period. And then a few million years later, the Earth gradually descended into this shorter Marinoan glaciation, which had sort of a more gradual onset and was much shorter, lasting roughly 15 million years from sort of 650 to 635 MA. So how do these snowball Earth events happen? Well, the most commonly proposed and accepted hypothesis is that of the runaway albedo effect. So runaway albedo is thought to have occurred due to reduced solar luminosity, which allowed ice sheets to extend from the poles down to about 30 degrees latitude. And this allowed a real reflection of the amount of sunlight the Earth experienced, which allowed then these ice sheets to extend down further, plunging into a snowball Earth period. But the Earth wasn't stagnant during these snowball Earth periods. Plate tectonics was still happening, volcanic outgassing was still occurring. So we still had this dynamic Earth under these ice sheets. But what that meant was that because of the ice on the Earth, you've got this real reduction in silicate weathering, which was using up CO2. But due to volcanic outgassing, you've still got relatively large amounts of CO2 occurring. And this gradually built within the Earth's atmosphere, up to the point where the amount of CO2 in the atmosphere could offset the albedo effect, causing rapid and violent deglaciation under greenhouse conditions. So I think it's useful to slightly dive into the timeline of the snowball Earth hypothesis, as this allows us to sort of set up the current problems that we've got still to solve in this climate state today. So if we go back to the 1930s, it was discovered that there was this sort of global distribution of Precambrian age glacial deposits. And these were found to occur on all 5 continents and be separated into 2 distinctive time intervals. So now what we know as the Sturtian and the Marinoan glaciations. Fast forward a bit further into sort of the 1970s, Anthony Spencer published his infamous memoir on the late Precambrian glaciation in Scotland. And this memoir was developed using field observations from the Garvellach Islands, which we'll hear about in a bit, and the Isle of Islay up in Scotland. And this memoir has really stood the test of time. 50 years later, you can still go back on these islands and use Tony's observations and really see what he was talking about still evident there today. Fast forward a bit further, in the early 1990s, we've now got an understanding of what plate tectonics was doing. And Joe Kirschvik proposed that this snowball Earth glaciation happened, where ice sheets extended all the way down to the equator. There was an insurmountable amount of evidence for this, which Joe was originally trying to disprove the fact that snowball Earth occurred, but the evidence didn't really allow him to do this. Gradually through the 1990s, this hypothesis gained traction, mainly led by Paul Hoffman and his work in Namibia, to try and understand what was happening in this climate state, but also to advance our understanding of how fast the Earth would have gone into a snowball Earth climate state and the speed of the deglaciation that occurred after this. And then moving on to sort of where we are in the present day, we have an understanding that this snowball Earth event likely happened, but ages for the deposits are still yet to be fully calibrated. So work by most of the snowball Earth focus team today has been focused on defining ages for these deposits to separate them into those that represent the Sturtian glaciation and the Marinoan glaciation, and to understand the completeness of the records that we have worldwide, to therefore understand Earth's dynamics during this time. So whilst the Earth flicks nicely between these sort of mainly 2, but also 3 different climate states, there's natural factors that drive the occurrence of these climate states. And the main sort of 3 big ones are solar irradiance, volcanic eruptions, and different climate phenomena. We're going to focus here mainly through this talk on solar irradiance, and climate phenomena. So starting with solar irradiance. So the Earth experiences different amounts of energy, which is governed by the amount of solar energy the sun's giving off, basically. And this influences atmospheric temperature, cloud formation, and global circulation patterns that we know of today. So these variations in solar irradiance occur due to sunspots, which are dark planet-sized regions that occur on the sun's surface, and they therefore give variations in the intensity of solar irradiance the Earth receives. And these sunspots occur in cycles due to variations in the sun's magnetic field. So every 11 years or so, the sun's magnetic field reverses, which gives rise to roughly 11-year cyclicity, which is known as the 11-year Schwabe cycle. And during a Schwabe cycle, you start with a period of solar minima, where you've got the minimum amount of sunspots, so minimum solar energy. Middle of the Schwabe cycle, you've got maximum number of sunspots, maximum solar energy, and then it decreases to a minimum again. So whilst this 11-year cyclicity is due to magnetic field reversals on the sun, that means that every 2 Schwabe cycles, you're back at the same magnetic field state you were to start with. So that gives rise to roughly 22-year cyclicity, which is known as the Hale cycle. But as well as this periodicity, the amplitude of those Schwabe cycles can also vary through time. But this occurs over much longer timescales, which gives rise to this 100-year cycle, which is known as the Gleisberg cycle. There's supposed to be images on there. They're not there. We're going to use our imagination here. So secondly, second importance to the sun driving our climate are different climate patterns, of which one of the most common and important today is the El Nino Southern Oscillation, or commonly known as ENSO. And ENSO occurs due to variations in sea surface temperature away from the mean state. And this has overall influences on sort of global atmospheric circulation patterns, but mainly the distribution of temperature and precipitation across the globe. So what you would have seen from the picture is that this occurs in the equatorial belt and it's mainly focused on the tropical Pacific. So if you've got an El Nino event, which is one of 2 different types of ocean events you can have, this is a warming of sea surface temperatures away from the mean state. This increases precipitation over the equatorial Pacific, and also comes with a decrease of the prevailing wind strength. And the opposite of that is a La Nina event, where you've got decreased sea surface temperatures away from the mean state. You've got an increase in rainfall and an increase in the strength of prevailing winds. You can also have neutral events where you don't really see any variation away from the wind, away from sea surface temperatures. And you get this sort of cyclicity that occurs between them on a roughly irregular cycles of sort of between 2 and 7 years. So these climate patterns are much more irregular than those very distinctive sun patterns on the last slide. And again, if you can use our imagination again, you would have seen a picture of prevailing wind directions here, which govern the quasi-biennial oscillation. So this is a much slower but more regular pattern in the Earth's climate system. And it's the most regular but slow variation that the Earth experiences after just a regular seasonal cycle that occurs. And this has overall influences on the distribution of atmospheric temperature that the Earth experiences. So this quasi-biennial oscillation is driven by a change in strength and direction of the winds, which occur above the equator, high in the stratosphere. So say, for example, these winds initially start going in an easterly direction. Every 14 months or so, these winds decrease in strength and then gradually reverse direction. So you get this sort of east-west-east pattern in prevailing winds, with this overall cyclicity of roughly every 2 to 2 and a bit years. We have no images at all now. I could really do with them. We have animations. Maybe not. I've got no image. Oh no, we did. Forgot my animation existed. Right, there's your El Nino and La Nina patterns, and there's your cyclicity occurring on roughly every 2 to 7 years, with the red and blue bits respectively. And there we go. There's your quasi-biennial oscillation. with your prevailing wind directions and your cyclicity roughly every 2 and a bit years. There we go, bit of a spoiler, we're going to look at lake sediments, but there we go. So the climatic variability that's generated through these different climate and solar cycles is recorded in the sedimentary record. But because these cycles have really high frequency periodicity, so you're looking at annual, inter-annual timescales mainly, you need a sedimentary record which has got really high resolution and records basically data on the intervals of sort of seasons to sort of yearly scales. So all of these archives in that image you can see there, so tree rings, ice cores, corals or lake or marine sediments are really useful at doing this for us. And these have been used throughout the Quaternary mainly to identify different climate drivers. They've also, some of them, so for example, lake and marine sediments can be used back through geological time as well. So like my spoiler showed you, we're now going to move to look at lake sediments because they're a really valuable archive because they're prevalent throughout the geological record and can show us information on seasonal to yearly scales. So lake sediments are generally also known as varves, where varves show annual resolution, where the yearly variation in climate produces these sort of distinctive layers you can see. So what's called generally a summer layer overall is represented by the white bars in that thin section image there, where you have this sort of lighter coloured, much coarser layer. And then when you flip to sort of the winter period, you get this generally thinner, darker, finer sediments occurring. And this provides you interannual sort of variability that you're recording. Sometimes they can also record seasons. It just depends on the response of your system to these climate drivers. And because you have time variable inputs driving sediment contributions through this time, like I've said, you can record all the climate drivers I've just showed you in these records. So varves in the Holocene are really spatially extensive. They occur generally pretty worldwide, but they tend to cluster together according to different types. So there are different types of varve, I should say. So you've got things like clastic varves, endogenic varves, biogenic varves, where different responses of the system produce different outputs. So we're going to focus mainly on clastic varves, which are variations in sort of grain size and composition in response to these annual variations. And these different types of varves cluster together. They might experience this similar climate or similar catchment geology, which allow them to do this. But whilst these are really prevalent throughout sort of the Quaternary and have allowed us to really understand Quaternary climate drivers, and especially sort of the more recent Pleistocene glaciation they've been really useful for. As we go back through geological time, the amount of deposits which record annual resolution dramatically decreases. And unfortunately, this limits our understanding of the magnitude and spatial extent of climate variability throughout geological time. So if we go back to the Precambrian, there's only about 5 known laminitic deposits which record any evidence of climatic cycles. This is an extreme number. If you look through the entire Phanerozoic, there are sort of a handful that do this. But seeing as we're interested in the Precambrian, we're going to focus on sort of the 4 that are on the screen here. And these deposits span from sort of 2000 MA, which is way pre sort of these Snowball Earth times, found in Canada, up sort of to the dawn of the Sturtian glaciation, so that longer Snowball Earth glaciation, around sort of 810 to 715 MA. And then we jump to these laminitic deposits occurring post-Snowball Earth by the Nama Formation. But what we don't actually have is any glacial annual resolution deposits that were deposited during a Snowball Earth time, which could therefore tell us about the existence, role and manifestation of these solar and climate cycles during these really extreme global glaciations. So that's what we're going to try and do. And unfortunately, whilst I've shown you that these deposits are really prevalent throughout the Quaternary, as you go back through geological time, you don't find that many, and especially cryogenian age deposits from Snowball Earth times are relatively good worldwide as well. But trying to find varves during this time is really difficult. But what's actually been found this year is the Garvellach Islands up in Scotland are a really useful archive of Snowball Earth, where they host deposits that record timings that aren't found anywhere else worldwide. So to sort of give you some geographic context here, the Garvellach Islands are up on the west coast of Scotland. They're a really small chain of islands, just south of Mull, just north of Jura, and they're composed of four islands, of which the largest you can see on that bottom panel there is Garvellach. And that island there is the big island you can see in that top image with the cliffs just beyond the boat. And then that bottom image there shows a view down the island chain. So Elias, who took this picture, was stood on the red dot there, looking down towards the arrow, where the first island you can see is Achuli, and then beyond that you get Aileach and Niamh. So you might have seen these islands on the news this summer, and Elias himself, as these Scottish islands have been found to record the most complete Sturtian Snowball Earth's sequence of glaciogenic deposits known worldwide. And through zircon dating, Elias has been able to show that we have a relatively complete record of Snowball Earth, or that Sturtian glaciation, from the pre-Snowball Earth dolomites of the Garvellach Formation at the bottom, and then you see the change into this Snowball Earth glaciation on these islands. And then as you walk along the island, you can see all the duration near enough of the Sturtian glaciation, but also importantly, the deglaciation that followed this. So hopefully, Elias has shown the global significance of these islands in studying Snowball Earth, and has hopefully provided evidence for these islands to be marked as a golden spike for the start of the Cryogenian period, hopefully to be decided next summer. And Elias at the bottom there is holding a carrot at the site that hopefully see the golden spike at after the Cryogenian subcommission have decided next summer. So we're going to dive a little bit into the geology of these islands now. So we're going to be looking at the Port Askaig Formation, which you can see on the log there. And this is a 1.1 kilometre thick formation that forms part of the Dalradian supergroup, which spans across Scotland and Ireland and is overall sort of 25 kilometres thick. The Port Askaig Formation makes up most of the formation that's present across the Garvellachs, and mainly Garvellach, which is the island we're looking at here. And the benefit of these islands to study this formation is that they dip really nicely about 30 degrees and they're young from north to south. So you can walk along and really follow up from pre-glaciation into this glacial formation. So the Port Askaig has, like I said, is about 1.1 kilometres thick, and that thickness is broken up into 5 different members. Throughout the different members, you've got 48 discrete diamictites, which are interbedded with sandstones, siltstones, and dollarstones. And overall, throughout this formation, you record 28 glacial episodes, 25 periglacial episodes, and 23 non-glacial episodes. So you can really start to see the advance and the retreat of the ice sheets and the dynamicism of this of Earth during the Snowball glaciation. So just a bit of a look at what the rocks look like in this formation. Like I said, you've got 48 diamictites, numbered from 1 at the bottom up to 48 at the top. And they don't really change composition through them, as you can sort of see on the photos. And they're sort of very standard, and they just vary in thickness. These are sort of interspersed with a lot of non-glacial strata, so that being siltstones, sandstones, dollarstones, and these vary in location and thickness through the sequence. But a thing that they have in common is they all have these really sharp contacts with this between the diamictites and that non-glacial strata. So overall, this formation is thought to represent advance and retreat of the ice front represented by those diamictites, but also periods of ice-free, shallow, marine, sort of maybe fluvio-deltaic sedimentation in this sort of open ice-free ocean as you go through the Port Askaig. So one of the most striking features and spectacular outcrops that you can see over the course of the Garvellachs is what's known as diamictite 13, and that's sort of in the middle of these this outcrop here. So this photo is taken from a boat looking at Aileach and Niamh, which is one of the smaller islands on the Garvellach chain. And you can sort of see this 200-metre long cluster of folded dolomite in the middle here. And that's known locally as the bubble. And this was folded and transported by these Sturtian age ice sheets during Snowball Earth. So this shows you the power and extent of the ice sheets which covered Earth during that time. But we're going to go and look at an outcrop that's slightly less spectacular. So the outcrop that's of interest to us is this isolated laminated siltstone occurring at the top of member 2 of the Port Askaig. You can see in that black box there. This is about 5.5 metres thick and has conformable contacts with white cross-bedded sandstone above and below. The best outcrop of this is denoted by that red star up on the southeast coast of Garvellach. But a set of laminated siltstones at equal stratigraphic height, but much thicker at about 9 metres, have also been found on the Isle of Islay, just south of the Garvellachs. So this is what they look like in outcrop. They look like laminites, basically. They're dense, laterally continuous, really thin laminitic deposits. And these occur for roughly 5.5 metres thick, but the outcrop itself is really laterally discontinuous, and you can see it pinching against sandstone about in tens of metres distance from either side. So these laminites vary in thickness, which you can see on the depth thickness graph in the middle there. They vary between approximately 0.3 millimetres thick and 21 millimetres thick. And the thickest laminites occur sort of in that bottommost metre, and then the mean thickness of these decreases as you go from base to top. So the most striking feature microscopically of these is that you get this consistent presence of coarse and light and dark laminae, there we go, which you can sort of see represented by the log there. So back in the memoir that was published in the 1970s, Anthony Spencer and George Warrington went and measured the thickness of all these varves in the field onto tracing paper. And this original thickness graph you can see on the screen now. And this encased 2,587 laminae. So this was quite an extensive job and covered nearly the whole 5.5 metre thickness of this. These outcrops are really well preserved, but this tracing paper is also even more well preserved. So this digitized thickness log was generated from those original thickness measurements that were made back in the 1960s. So we took a sample of these laminites from roughly halfway up this section on Garvellach to have a look at what was going on microscopically and sedimentologically. So here you've got 3 different photographs showing these laminites at 3 different scales. So this is what they look like in the field, and then we've got a thin section photomicrograph, which was stitched together on microscope, and then just a sort of a bog standard high resolution thin section photo. And as you can see, the most striking feature of these laminites is that consistent presence of light and dark laminae, which shows this really regular alternation. The thickness of these you can see varying. You sort of get these periods where the laminae are relatively thicker, and then these clusters of relatively thin laminae around this box showing C here. And in some of them, although you can see these sort of light and dark laminae, in some of them you can sort of see this really weak single internal stratification in the middle of that coarse laminae. But that doesn't occur in all of them, but it does occur in some of them. So these lighter laminae, as you can see by the thin section photos, show normal grading from sort of fine to very fine sand through them. And that's a consistent feature of these. But also along the bases of quite a lot of the laminae, you get these medium sort of coarse-grained, relatively well-rounded quartz grains, which show this sort of general alignment, sort of with an east-west orientation. They don't occur to the same density on all of them. As you can see in that picture C there, those ones there's quite a heavy concentration of them, but that amount does vary through the sequence. And then when you go to the finer laminae, these don't show any grading really at all. They're mainly composed of silt and clay, and they're consistently a lot thinner than these coarse laminae. And then at the boundary between these coarse and light laminae, you tend to get these quartz grains occurring again. They tend to be much coarser this time, and they tend to displace the silt layer above them. So the origin of these laminites has been contested. Not a lot of work is done on them, but there have been different opinions on their origin. And whilst we don't focus on the origin is important to understand the duration of which they preserve, and therefore important to understanding what periodicities are present within these laminites. So an unpublished paper from back in the 1960s worked on these Garvellach laminites and found evidence that they were glaciotidal origin. The people that worked on these were mainly physicists, and they took into account that the Port Askaig Formation overall was thought to represent shallow marine, tidally influenced deposits. So they thought that, well, tidal influence must be of importance in the origin of these laminites, which are bounded by tidally influenced sandstones. Tidalites aren't uncommon during Snowball Earth glaciations, but they're more commonly occurring in that shorter Maranoan glaciation, of which one of the most famous formations is the Laminated Formation in Australia, where you can see really clearly here that you get these sort of bundles of thinner laminae bound by these much thicker, finer layers, represented by the ends and the little arrows on that image on the left there. And tidalites record diurnal sedimentation in response to sort of spring and neap tide cycles, which occurs on a fortnightly to monthly basis. So that shows you how rapid the sedimentation was occurring during the deposition of the Laminated Formation. But if you compare that to what we've got of the Port Askaig Formation, you can see quite a distinctive difference in the structure of these deposits, where we have really clear individual coarse and fine laminae rather than this bundle structure. And if you also take that in context of Scotland's paleogeography during the Sturtian glaciation, so Scotland was situated roughly at the red star on that map on the right-hand side there, in a secluded location between Laurentia and Amazonia. So it wasn't subjected to the open ocean. But also it's been found that during this Sturtian glaciation, there was extremely weak tidal amplitudes, up to the point where sort of no tidal processes were thought to have been occurring in open ocean locations. So taking this alongside this secluded location and these individual texturally distinct laminae, we sort of interpret these as annual glaciogenic lacustrine varves. So we predict that these are of annual duration, and these are this duration was produced due to seasonal variations in glacial meltwater, which would have deposited these. So it's highly likely that that coarse lighter layer of that thicker layer of the laminae was deposited during sort of active sediment-laden underflow currents from sort of this glaciofluvial systems, which basically submarine flows into this lake basin, which deposited this fining upward sequence. But these were discrete discharge events. So after this discharge occurred and the underflow settled, you then get that fine sedimentation occurring from sort of rain out from these overlying layers and from the lake sedimentation in general. But also because we've got those coarse quartz grains which are occurring throughout these laminites, it's highly likely that this is ice-rafted debris, not necessarily from the ice sheet itself, because you're looking on coarse grain scale rather than sort of dropstone scale. But most likely because this represents that the lake surface is most likely frozen during this time. So during the winter, you get these sort of wind-blown particles onto the surface. You get this spring thaw, this ice melts, and you get this rapid rain out of these grains, which is why you see them along the basis of these laminae. And these annual varves then sort of suggest that there was an active hydrological cycle occurring during the Sturtian glaciation. So annual varves aren't necessarily unreasonable because you still would have seasonal melting occurring during the Sturtian glaciation. And it was sort of hypothesized that you would get more effective seasonality on a solid Earth because of extreme continentality. So if we put these deposits overall into where they sit in the Port Askaig Formation, you can see an architectural panel on the right-hand side there. So the varves that we're looking at are on the east coast of Garvellach. So they're in the red box there, represented by that dark green laminitic section there. And as you go up through that sequence, you get this laterally discontinuous moraine deposited known as D32, which you can see pinching out by the end of that red box. This is conformable with what's previously been interpreted as fluvio-deltaic sandstones, which are then conformable with our glacio-lacustrine varve sequence, and then conformable again with these sandstones at the top. So it's overall been interpreted, these deposits are part of sort of either a moraine dammed or deltaic deposit dammed glacial lake, which represented multiple stagnant small-sized bodies of water on a subaerial relatively flat surface. So the common analogue that's used for this environment by different people on Snowball Earth was that of the Mackenzie Delta today. So now we've sort of looked at the duration of these laminites and what duration of sedimentation they're recording. We can start to look at the cycles that are present and start to interpret these in terms of what they represent. So the thickness series of the Garvellach laminites that you can see on top there was initially studied for evidence of cycles back in the 1960s, but no statistically significant periodicity was recorded within these laminites. So we redid the spectral analysis based that we've got higher computing power today and this digitized time series. So we conducted this in the stratigraphic domain using a bed number series of varve thickness, which then gave us a power spectra you can see on the bottom there with frequency in cycles per laminate. But assuming that these have a duration of years, you can then interpret that each of these cycles on there is represents a number of years here. So we can see at the 99% confidence level, there's 7 peaks which are coming across. And these are sort of represented in the bundles of sort of between 2 and 2.5, 3, 4, then 16 and 136. You also do get cycles coming through at the 95% confidence level. And you can see the ones which are at 99 here are shown in bold, and the ones at the 95% are shown in non-bold text. So if we start to look at what these cycles might represent, we can see that we've got interannual, decadal and multi-decadal cycles coming through in this power spectra, which sort of have periodicities similar to that we see within quaternary deposits. So starting on the very high frequency end of the scale, you've got frequencies that could be associated with sort of the Precambrian equivalent of sort of the quasi-biennial oscillation. Sort of the periodicities between like 3 and 5 there could be a Precambrian equivalent of the ENSO variation. Going up a bit higher to our decadal cycles, those between roughly 9 and 16 could be equivalent to that of the Schwab cycle. And then our multi-decadal cycles that we see there could be the equivalent of the Gleisberg cycle. So we see a variety of periodicities evident within this time series that represent both sort of solar forcing and climatic forcing that controlled, potentially controlled deposition of these varve units. So what we know from what we can see from that image on the left is that our overall varve thickness, you get this much thicker coarser layer and this much thinner finer layer. And the thickness of that fine layer throughout the whole varve sequence is relatively small and also relatively constant. So the total thickness variation of these varves can be ascribed to that of the coarser layer. So whilst we don't have the data necessarily to do this, it's highly likely that if we conducted spectral analysis on the light layers and the dark layers respectively, these climate cycles that we see would be of statistically significant periodicities within the light layer, but then within the dark layer, you might not see any periodicity because this fine layer is just adding noise to the data set by stochastic sedimentation. And this has been found in other examples of varves where your overall periodicity, So panel C here shows these cycles, but you can separate these into what's occurring. So overall, if we're then attributing these climate cycles to that of the summer layer, you can see that then these periodicities of solar and climatic forcing are controlling summer cycles in that glacial cycle. So let's start to look at the stability of these cycles during global glaciation. So we're going to start with these longer term solar cycles. And the sun is well known to be one of the most important drivers of the climate on Earth. So we found that we have evidence of both the 11-year Schwab cycle and this sort of centennial scale iceberg cycle in these deposits. As you can see by that plot on the left there, it's really common throughout geological history to sort of have evidence of this 11-year Schwab cycle occurring at roughly the same periodicity, but also then evidence of that 22-year hail cycle coming through. So we don't necessarily have evidence of the hail cycle, as we have no statistically significant periodicity at roughly 22 years, but instead we have this longer iceberg cycle preserved. Whilst this has been found a couple of times, you can see by studies number 11 and number 8 there, in sort of the Paleozoic and Mesozoic, this cycle isn't necessarily preserved by the time you get back to the Proterozoic. So we think we have this cycle because we've got a really quiet depositional environment here with high sedimentation rates. But we also have a real long time series here. So we've got nearly 2,600 years worth of data preserved in these sequence, taking that these valves are of annual origin. But studies which have done similar analysis using different valve units throughout geological history might only have much smaller number of valves to use in spectral analysis, where sort of common numbers are between sort of 500 to 700 valves. So we've got a much longer time series, which allows for many more iterations of this cycle to be preserved, which allow it to stand significant above the generic noise that's produced by stochastic sedimentation. However, one of the potential onset factors that was thought to be significant in causing Snowball Earth was that of reduced solar luminosity. So it was predicted that solar luminosity was between 85 to 95% of the present day level, which allowed those ice sheets to extend and then us plummet into a Snowball Earth. So what we can sort of see here is that even though we've got this reduced solar luminosity, the stability of these solar cycles is still present, which is then allowing glacial fluctuations to respond to this and be of an amplitude that these sediments can then record. So if we go on to discussing the origin of the climate phenomena in this. So whilst we can't say that these cycles are exactly equivalent of that of the modern day ENSO and quasi-biennial oscillation processes, because the paleogeography was different and these exact processes with this exact operational mechanism would not have probably existed. But we can see that there was a similar climatic phenomenon producing variations in temperature and precipitation that was occurring during Precambrian time. So the exact conditions, both oceanographically and geographically, for the modern day ENSO and quasi-biennial oscillation didn't arrive until sort of Mesozoic times. But what you can see from that climate archive animation on the left there is that you've got variations in the jet stream, ocean circulation, precipitation and temperature occurring through geological time, and especially in this sort of equatorial belt. And despite loads of different paleogeographical variations, these variations still occur. So it was highly likely that you've got climatic phenomena operating on very similar periodicities, causing changes which could be preserved in sediments in a very similar way. So whilst I've talked about both solar and climate cycles separately, it's highly likely that these didn't influence sedimentation separately, but were actually linked together and both drove sedimentation patterns during this glaciation. So there's been common links between sort of mainly the 11-year Schwab cycle and climate phenomena that have started to be developed. But the processes driving these and the links between them are still under contention at the moment. It's a complicated factor. But there's been found to be links between this 11-year Schwab cycle and the ENSO variation, where you get these moderate to strong El Nino episodes occurring during these periods of solar maxima, which could have both exerted an increased amplitude in the sedimentological record. But also there's been links between the solar cycle and the quasi-biennial oscillation, where this variation in amplitude of the quasi-biennial oscillation seems to follow that of the solar maxima and minima of the solar cycle. So it's highly likely that you've got both of these processes operating together to drive variations in atmospheric and oceanic circulation patterns, which are then modulating climate dynamics and being recorded in the sedimentary record. So overall, what we can see is that we've sort of filled in that gap that was present in the Neo-Proterozoic. So we've got evidence of sunspot and climate cycles occurring at the dawn of the Sturtian glaciation. And then we show that these cycles exist, are manifested in the sedimentary record, and remain stable during that Sturtian glaciation. And then afterwards, the Nama formation shows that these cycles remained consistent post-Sturtian glaciation. So what we can say roughly is that what these cycles have been evident since the Neo-Proterozoic, and they continue on to be measured quite happily in the present day. So it's likely that these solar climate interactions have modulated climate throughout the Earth's entire history and will continue to modulate climate however it changes into the future. So overall, what we've seen is that the varves of Garvellach represent annual sedimentation, and this most likely deposited in sort of a glacio-lacustrine setting and provide insight into Neo-Proterozoic climate variability during that very specific time that we were missing in the Snowball Earth period. And also the presence of both solar and climate cycles sort of provides evidence that these were stable during glaciation, despite processes which may have altered these. And these solar and ocean and atmospheric dynamics modulated sedimentation driven by glacial dynamics and provide evidence for an active hydrological cycle during these global glaciations. And that's the end of me.
Well, thank you, folks. Anne, have any questions?
Great talk, thanks. I really appreciate the historical perspective of your study area. It's really interesting, cool rocks, and very interesting interpretation. As a non-sedimentary geologist, can you help me understand something? When I think of Snowball Earth, and I think of Antarctica or Greenland, I think of hundreds of meters or kilometers of ice. And I don't necessarily think of deltas and lakes and ponds. So in my mind, it's really difficult for me to see this transition in sequence from these glacial deposits to these other deposits like you're showing. So is the temperature varying that much where you get large scale retreated ice sheets, or help me understand the actual transition and depositional environments? If you can, thanks.
I can try and provide some insight. There are people that will understand this much better than me. So whilst this glaciation was thought to have occurred for 60 million years continuously, there's different hypotheses behind this. So you've either got the solid Snowball Earth hypothesis, which claims that ice sheets extended from the poles to the equator, basically froze the entire ocean, so it acted as one solid body. Or there's interpretations that there was more of this slush ball Earth, which is where you have sort of more ocean dynamics than we expected to occur during the Snowball Earth glaciation. But sort of either hypothesis that you sort of take, it's been interpreted that during this, you will still have sort of glacial and interglacial cycles occurring because you've still got climate drivers occurring during this time. So if you've got variations in solar luminosity during that time, which drive ice sheet volume, if your ice sheet volume decreases, you're going to then have ice sheet retreat, or the ice sheet extent will decrease. So then you're going to move from them one deposition environment, which might have deposited a diamictite straight at the end of that glacier, into the adjacent environment. And here, sort of the area that we're looking at is sort of the ice sheet ocean interaction interface, really, where you're still going to have oceanic and marine sort of sedimentation processes occurring during that time when the ice sheet wasn't there. So you've got that sort of those diamictite periods which show you the extent of the ice sheet, and then the associated marine sedimentation will just sort of tell you whereabouts you are in relation to that ice sheet. So you're still going to.
It's correct to it's correct to think of this more as like you know, not hundreds and hundreds of meters of ice on the continent, but something more like something more similar to what you'd see, I guess, sort of on the coastline of Greenland or Iceland.
Potentially, this is not my expertise overall.
Celestial Earth helps me kind of visualize it a little bit better.
But you're gonna have these different environments of different sedimentation occurring throughout this whole time. And your ice isn't gonna, like, your Earth is dynamic during this time. Your environment isn't gonna stay stagnant. You're gonna have these variations. It's just they'll be more pronounced in some areas than others. So some areas worldwide you've got much greater thickness of diamictites where your ice sheet was thicker, but we're in the equatorial latitude around here trying to discern what was happening. So it's more likely that you're very on the limit of ice sheet extent where you can record this variation in sedimentation.
Okay, that's very helpful. Thanks.
That's okay.
Yeah, you were showing the paleogeography there.
Yes.
But it's very controversial background there, you know, you've got these arguments of huge true polar wander events and all sorts.
Yeah.
Has anyone done the paleo in these particular rocks?
Don't think so.
Wow.
Not as far as I've read, no.
Someone will see. Yes.
I imagine so. These particular rocks have been documented quite heavily in terms of sedimentology, but I don't think I've seen any paleomag of them.
John Sarling, I think, Simmons,
There we go.
and somebody from
I
Mexico.
tried to research.
Oh, yeah, there was some oddities about this study.
Yeah.
I think Charles Dr. London's the fact is.
So yeah, I guess it's very interesting you find these solar cycles with the same duration. You touched on it a bit with the kind of strength expecting a kind of weaker sun at that time. Are there sort of any observations from astronomy or like modeling that shows that these solar cycles should be the same length for hundreds of millions of years at that amount of time? Is that kind of expected?
Based off my experience is a record of solar cycles preserved in lake sediments throughout geological time. So from that point of view, the solar cycles have remained relatively stable. Where if you look in Precambrian records, but also Quaternary records, it's found that sort of the variability on that that 11-year solar cycle is mainly sort of between 8 and 16 years, with your average at 11. And then your Gleisberg cycle is slightly more variable, anywhere between sort of 90 and 140 years, but generally relatively constant. And this is thought to be constant throughout geological time. It's your climate oscillations that are slightly more unpredictable because you've got much bigger variations which can drive them.
Go for Richard's question because he has just had something.
With the same confidence limits, this means we would expect 1 in 20 of the periods to be significant at random. This would seem to account for the observations, so are they really significant?
It's a good question. Based off the evidence and based off field evidence, you can see evidence of cyclicity in these deposits. You can see that a few of these cycles only just reach over these limits, and you have to account for background stochastic sedimentation that occurs. And you also have to account for the fact that these rocks are 700 million years old, and we don't know stratigraphic completeness of these entirely, and especially if we're taking annual origin, you don't know also whether these have been measured correctly. I mean, we're using a time series which was from the 1960s, which we assume was measured correctly. We don't know. We're taking that you can see these, and we're trying to interpret them if they were statistically significant, but we appreciate that there's uncertainty and error on the boundaries of whether these actually are or not.
One last question.
Rachel, I was interested with the quartz isotopic debris / drop stones. I'm not sure how much the sequence you've got in thin section, but would you expect the frequency of dropstones also to preserve some sorts of climate indicator as well?
Yeah, that's one of the things that we've noticed is that it seems like there's cyclicity in the amount of rock grains that are occurring through the sequence. We have 10 centimetres of thin section to about 5.5 metres of outcrop. So we started to gradually look at this, but we're hoping to go and drill it in May. Whether that actually happens, we're not sure. And then hopefully we can start to make something slightly more conclusive out of that.
I think